Luminosity is the total energy output per second in all directions. So if you could put a net around the sun and capture all the photons coming out of the sun every second, that'd be the luminosity of the sun. Brightness, on the other hand, has to do with how much energy is coming out per unit area every second. So if we look at the sun and we see how much energy is coming out of 1 square meter of the sun, that will be the brightness of the sun. Now, surface temperature of stars determine their brightness. Spectral class of the stars is also determined by surface temperature. The hotter the star, the brighter the star. Of course, we're talking about surface temperatures because that's all we see. We don't see the core of the star. Two things determine the luminosity of a star. One is the surface area of the star. The bigger the star, the more surface area it's going to have. So if two stars are the same temperature, the one that is bigger will have more luminosity. Second thing that determines the luminosity of the star is the surface brightness of the star, which is dependent on the surface temperature. So if you're two stars and one star is 12,000 degrees Kelvin, one star is 4,000 degrees Kelvin, and they're both the same size, the one that is 12,000 degree Kelvin is the one that is more luminous. In 1920s, two men, Dr. Hertzsprung and Dr. Russell, they did research on the luminosity of the stars versus their surface temperature. And what they came up with is called a Hertzsprung-Russell diagram. It turns out that if you plot the luminosity of a star with its surface temperature, that they all fit in this beautiful pattern here. This is called the main sequence of the stars. Main sequence of the stars are stars that are very stable. They fuse hydrogen into helium, and the sun is one of them. And stars live on the main sequence until they start evolving, becoming a giant, red giant, subgiant, or what have you. The surface temperature of the stars are easier to remember if we can classify them according to the surface temperature. So we have something called spectral classes of the stars. These spectral classes are also telling us what color the stars happen to be. As an example, the O stars are stars that are hotter than 30,000 degrees Kelvin. The color appears to be blue. B stars, cooler, between 10,000 and 30,000 degrees Kelvin on the surface, and they're blue-whitish. Now, if you go down the list here, the sun is a G-type star, and the M-type stars are the reddish orange type stars. The spectral classes of the stars can be remembered by remembering the sentence, "Oh, be a fine girl and kiss me," or "Oh, be a fine guy and kiss me." Not only the O stars are brighter than the B stars, but the O stars are also more massive than the B stars. The O stars are also more luminous than the B stars. The O stars are also bigger than the B stars. So as we go from the O stars to the M stars, we have less and less and less mass, M stars being the least massive of all the stars in the sky. O stars are the most massive of all the stars in the sky. It also tells us how long they will live before they leave the main sequence of the stars and become evolved stars like red supergiants and red giants. It turns out that the O stars don't live very long. They live the shortest amount of time. The M stars live the longest amount of time. So the O stars can be as big as 200 times the mass of the sun, and they live just for a couple of million years. M stars, on the other hand, they're pretty cool on the surface, and something like 3,000 degrees Kelvin on the surface, but they live forever, basically. They live about 1 trillion years. At least the cooler ones live for about 1 trillion years.